Hey there. Welcome to our channel. We're so glad you're here. Please like, share, and subscribe to join us for awesome content. Also share this video with your family and friends. Let's get started. You are floating, not in water, not in air, but in the quiet between the stars. Around you, the universe breathes, vast and patient. A dark ocean with no surface, no floor. Above, below, in every direction. There is only the soft glow of distant suns, each a tiny flicker against the endless. You might think of them as lanterns, because that is what they are, beacons. Not just balls of burning gas, not just nuclear furnaces, but guides. Each one holds its own court of planets, moons, asteroids, worlds upon worlds, drifting in the great cosmic tide. And there are so many. The numbers alone could dizzy you. Our galaxy, the Milky Way, cradles over 100 billion stars, 100 billion suns, 100 billion chances for planets to form, for chemistry to stir, for just maybe something to look up and wonder just as you are wondering now. But let's not rush. Let's stay here in the quiet just a little longer. Close your eyes or keep them open. It makes no difference in this darkness. Imagine the closest star to us, Proxima Centauri, a red ember just 4.24 light-years away. That means its light, the very photons dancing against your eyelids right now, left its surface 4 years ago. When they began their journey, you were different. The world was different. And yet, here they are now, reaching you, a message from a place you've never seen. Now imagine this. For every grain of sand on every beach on Earth, there are 10,000 stars in the observable universe. 10,000. Try to hold that number in your mind. Feel its weight, and then let it go. Because the truth is, no mind was meant to grasp such things all at once. So instead, think of it like this. You are adrift in an ocean where every drop of water is a sun. Some are blue-white and searing, young and restless. Others are old, cooling to red, their light a slow exhale. Most are smaller and dimmer than our own sun, their warmth a faint touch against the faces of any worlds that circle them. And some, so faint they barely glow at all, are failed stars, caught forever between planet and sun, their light a whisper. But here's the wonder. Every one of them could have planets. Once we didn't know this. Once we thought our solar system might be rare, a fluke of cosmic architecture. But now we know better. Planets are not the exception, they are the rule. Wherever a star forms, wherever dust and gas swirl into a newborn sun, worlds follow. Like moths to flame, like birds to a branch, matter clumps and gathers, and soon, over millions of years, spheres take shape. Some are giants, thick with storms, their gravity so strong they sculpt the paths of other worlds. Some are small, rocky, quiet. Some are ice, some fire, some so strange we don't yet have names for what they might be. And yet, for all their variety, they share one thing. They are all under a sky. Every planet, no matter how distant or alien, has a horizon. A place where its sun rises, where its moons set, where its atmosphere, if it has one, filters light into colors we might not even have words for. What would it be like to stand on such a world? To look up and see not our familiar sun, but a different star, painting the clouds in unfamiliar hues? To feel the tug of a gravity just slightly stronger or weaker than the one that holds you now. We don't know yet, not for certain, but we are learning. Telescopes peer into the dark, catching the faintest dips in starlight as planets pass before their suns. Spectrographs dissect the glow of alien atmospheres, hunting for the fingerprints of water, methane, oxygen. The whispers of a world that might, just might, cradle life. And with every discovery, the universe feels just a little less lonely. Because if planets are everywhere, if they outnumber the stars themselves, then surely some of them must have shores. Not like ours, perhaps. Not sand and salt and tide, but something. Something that, in its own way, is just as beautiful. And if they do, well, that is a thought for another night. For now, let the stars above you blur into soft, glowing streaks. Let the darkness hold you. And as you drift, remember, You are floating in an ocean of worlds. Somewhere out there, another sky is waiting. For most of human history, the night sky was a map of fixed points. Stars were thought to be eternal, unchanging mere backdrops to the wanderings of planets like Mars and Jupiter, which danced across the constellations on their own mysterious schedules. The idea that other suns might have worlds of their own was pure speculation, a dream for poets and philosophers. Then, in 1995, everything changed. It began with a wobble, not a dramatic shake, not a visible shudder, but the subtlest of tremors in the light of a star called 51 Pegasi, 50 light-years away. Astronomers Michel Mayor and Didier Queloz, peering through telescopes in the south of France, noticed something peculiar. The star's light shifted ever so slightly, first toward the blue, then toward the red, in a rhythmic, repeating pattern. Like a dancer swaying in place, pulled gently by an unseen partner. The explanation? Planet. Not just any planet. A giant, half the mass of Jupiter, orbiting so close to its star that a single year lasted just for Earth days. A world so unlike anything in our solar system that it defied all expectations. They called it 51 Pegasi b, and with its discovery the universe opened wide. Imagine holding a child's hand and spinning in place. As you turn, their small weight tugs at you, forcing you to adjust your balance. You don't stay perfectly centered, you wobble just a little around the shared point between you. Stars do the same. A planet's gravity doesn't just keep it in orbit. It also pulls back on its star, making it sway in a slow, cosmic dance. This motion is tiny. A star might move at walking speed or slower, but it leaves fingerprints in the starlight. By measuring the subtle shifts in color, blue as the star moves toward us, red as it drifts away, astronomers can detect these invisible companions. This is the radial velocity method, the first way we learned to listen to the whispers of distant worlds. But wobbling stars weren't the only clue. Another method soon joined the hunt, the transit method. Picture a moth circling a porch light. If you were watching from far away, you might not see the moth itself, but every time it passed in front of the bulb, the light would dim just a little. Planets do the same. When they cross in front of their star, they block a fraction of its light. For a gas giant like Jupiter, the dip might be 1%. For an Earth-sized world, it's a mere 0.01%, like detecting a single raindrop in a downpour. Yet we can. NASA's Kepler Space Telescope, launched in 2009, stared at one patch of sky for 4 years, watching 150,000 stars for these infinitesimal flickers. It found thousands of planets, some rocky, some gaseous, some orbiting 2 suns at once, their shadows crossing in an endless celestial ballet. With these discoveries, something profound shifted. Our solar system was no longer a solitary example. It was just one configuration in a galaxy overflowing with possibilities. Hot Jupiters, super-Earths, water worlds shrouded in steam, planets with years shorter than a week, and others so distant they took centuries to complete a single orbit. And yet, for all their strangeness, these worlds followed the same laws as ours. Gravity bound them, starlight warmed them, chemistry shaped them. They were different, yes, but not entirely alien. Which raises the question, if planets like ours exist, could life like ours exist too? That mystery would take more than wobbles and shadows to solve. It would require peering into the very air of these distant worlds, reading the stories written in their atmospheres. But that is a story for another night. For now, let the stars above you blur into soft, glowing streaks. Let the darkness hold you. And as you drift, remember, every wobble, every flicker of light, is a message from a world waiting to be known. There is a place in every solar system where the light is just right. Not the scorching blaze of a star's close embrace, not the feeble glow of its distant reach, but somewhere in between. A band where warmth lingers like a held breath, where water could pool into lakes, where chemistry might stir itself toward life. Astronomers call this the habitable zone. But perhaps a better name is the Goldilocks zone because, like the porridge in the old fairy tale, it must be neither too hot nor too cold, but just right. Imagine standing by a campfire. Step too close, and the heat prickles your skin, driving you back. stand too far, and the chill creeps in, leaving you shivering. But there's a sweet spot, close enough to feel the warmth, far enough to stay comfortable. A planet's habitable zone works the same way. For a small, cool red dwarf star, this zone huddles close, so near that a planet there might be tidally locked, one side forever day, the other endless night. For a massive, blazing blue star, the zone stretches wide, but the star itself burns out too quickly for life to take hold. Our sun? It offers a gentle middle ground. Earth orbits squarely in its Goldilocks zone, where sunlight coaxes water into liquid form but doesn't strip it away into steam. Why does water matter so much? Because it is the universe's favorite solvent, the ink with which life might write its story. It dissolves, carries, it shapes. In its liquid form, it lets molecules meet, react, build. Too close to a star, and water boils into vapor, escaping into space. Too far, and it freezes solid, locking away its potential. But in that narrow, glittering band between fire and ice, it can persist, a shimmering invitation to chemistry. We've found worlds here already. Kepler 186f, 500 light-years away, orbits a red dwarf in the habitable zone, a rocky world that might glimpse an eternal sunset. TRAPPIST 1e, slightly larger than Earth, circles its dim star in a system with 7 planets, 3 of them in the zone. And then there's Proxima Centauri b, our closest exoplanet neighbor, bathed in the faint crimson glow of the nearest star to the sun. But habitable zone doesn't mean inhabited. A planet could be the right temperature and still be barren, scorched by flares, stripped of atmosphere, or simply lacking the right ingredients. Or it could harbor life in forms we've never imagined, thriving in ways that defy our earthbound expectations. How would we know? The answer lies in the air. If life reshapes a planet's atmosphere, as it has on Earth, filling our skies with oxygen, then perhaps we could detect its fingerprints from afar. A mix of gases out of equilibrium, a whisper of chemistry that shouldn't happen without something stirring it. That search is just beginning. Telescopes like the James Webb Space Telescope are training their gaze on these distant skies, hunting for the faint spectral lines that might say, here, something is here. For now, the Goldilocks zone is a theory, a hope, a celestial maybe. We know the conditions that nurtured life on Earth. We do not yet know if they've done so elsewhere. But the universe is vast, and time is long. And if there is one lesson the stars have taught us, it's this: where life can find a way, it often does. Close your eyes and remember the most beautiful sunset you've ever seen. Perhaps it was over an ocean, where the sky melted into liquid gold before deepening to violet. Maybe it crowned a mountain range, the peaks etching black silhouettes against a fading amber glow. That daily miracle, when sunlight slants through miles of atmosphere, scattering into colors, is as familiar to us as breath. But what if the sun were different? Sunset on Earth is a performance of light and air. As our star dips below the horizon, its rays must travel farther through the atmosphere before reaching your eyes. Shorter blue wavelengths scatter away, leaving the longer reds and oranges to paint the sky. The exact hue depends on countless factors: dust from distant deserts, moisture in the air, even the ash of faraway wildfires lending a deeper crimson. Now imagine standing on TRAPPIST 1e, a potentially rocky world orbiting a dim red sun. Here, the parent star glows not yellow but deep carmine, a smoldering ember in the sky. Its light is weaker than our sun's, just 0.5% as bright at noon. Yet at sunset, when that faint red light filters through the planet's atmosphere, if it has one, the sky might bloom in shades we have no name for. Not gold, not orange, but perhaps a deep umber, or a twilight that lingers for hours in perpetual dusk. A planet's atmosphere is both artist and canvas. High-pressure nitrogen worlds could bend light so severely that the sky appears to curve inward, with double sunsets miraged above the horizon. Thin carbon dioxide atmospheres might scatter blue light so efficiently that midday skies appear turquoise, while sunsets blush ultraviolet. Tidally locked planets with permanent day and night sides could host eternal dawn at the terminator line, a band of rose-gold light where winds howl between extremes. Even our solar system hints at these possibilities. Mars' tenuous atmosphere turns its sunsets blue, as fine dust scatters the red light away. On Titan, where methane reigns through nitrogen skies, the setting sun, if visible through the haze, would cast anemic yellow shadows across hydrocarbon dunes. These colors aren't just beautiful, they're clues. Astronomers use spectroscopy to dissect the light passing through exoplanet atmospheres. Each molecule leaves dark fingerprints in the rainbow. Oxygen signs potential life. Sodium and potassium speak of evaporated rock. Methane whispers of geothermal vents or biological activity. When James Webb Space Telescope analyzed the gas giant WASP-39b, it found carbon dioxide, water vapor, and even sulfur dioxide, the first whiff of alien weather patterns. One day, we may detect an atmosphere where the chemical cocktail suggests something improbable. There is a world somewhere, perhaps thousands, with sunsets unlike anything Earth has ever seen, where purple dawns stretch across icy plains, where twin suns dip below jagged horizons in synchronized amber farewells, where the very air fluoresces under the glare of a white dwarf, painting nights in ethereal silver. We haven't seen them yet, but every twilight here is a reminder. The universe has more colors than we've dreamed. Imagine the solar system as a grand orchestra. The sun stands at center stage, its gravity the conductor's baton keeping every instrument in time. Mercury's quick staccato orbit, just 88 Earth days. Neptune's slow, deep bass note, one revolution every 165 years. And Earth, a steady middle C humming along at just the right tempo for life. Now picture another orchestra, one where Jupiter-sized planets pirouette dangerously close to their stars, completing orbits in hours, where binary stars whirl around each other, their gravitational waltz flinging planets into elliptical loops, where moons strain against their planet's pull, their rocky bodies kneaded like dough by invisible hands. This is the symphony of gravity, and its music shapes everything. Every object in space moves to gravity's rhythm. Orbits are simply falling with style, a planet forever missing the ground as it curves around its star. Tidal forces arise when gravity's pull is stronger on one side of a world than the other, stretching it slightly. Resonances occur when orbital periods sync up, like Jupiter's moons Io, Europa, and Ganymede, locked in a 1:2:4 dance. These rules apply whether the dancer is a pebble or a planet. Some exoplanets move to astonishing beats. Hot Jupiters like 51 Pegasi b orbit so close that their years last days, their atmospheres boiling away under stellar fury. Eccentric giants follow oval-shaped paths, alternately freezing and frying as they swing far out then plunge close in. Trojan planets share orbits, forever chasing or fleeing gravitational safe zones called Lagrange points. The most fascinating cases are tidally locked worlds, planets where one face always stares at its star, like the moon to Earth. On such a world, the dayside bakes under eternal noon. The nightside sinks into permanent frost. Only the twilight band in between might know balance. Could life exist in these gravitational extremes? Perhaps. Around red dwarfs, small but tempestuous stars, planets must orbit dangerously close to stay warm. This subjects them to tidal heating, like Jupiter's moon Io, its volcanoes erupting from gravitational kneading, flare erosion, atmospheres stripped by stellar tantrums, locked rotations, one side always day, one always night. Loving this? Hit that subscribe button to keep up with our videos. Also share this video with your family and friends. Yet life on Earth thrives in crushing ocean depths, acidic hot springs, even nuclear reactor runoff. If chemistry can find a way here, why not on a world stretched by gravity's hands? As you read this, the moon retreats from Earth at 3.8 centimeters per year. Mars moons spiral slowly toward their planet. Our entire solar system orbits the Milky Way's core at 230 kilometers per second. Gravity's composition never ends. Its movements write the destinies of worlds, which ones become gas giants, which freeze as ice balls, which might, just might, hold something that looks up and wonders. Breathe in. That simple act connects you to the entire history of our planet. The oxygen you inhale was exhaled by ancient ferns, The nitrogen cycled through countless thunderstorms, the trace argon lingering from Earth's violent birth. Our atmosphere is a living archive, each molecule a page in a story 4 billion years in the telling. Now imagine another world's breath. An atmosphere speaks in subtle ways. The thickness determines whether sunlight kisses the surface or gets lost in haze. The composition reveals whether oceans evaporate or volcanoes still rumble. The circulation shows how heat dances between day and night. Take Venus, Earth's twisted sister. Its thick CO2 cloak traps heat in a runaway greenhouse effect, while sulfuric acid clouds race around the planet faster than hurricanes. One breath there would crush, burn, and poison you in seconds. Yet on Mars, the whisper-thin air, just 1% of Earth's pressure, lets radiation scour the surface unimpeded. Its rust-colored skies occasionally stir with dust devils tall enough to dwarf our tallest buildings. These are our neighbors. The true aliens lie farther afield. When an exoplanet passes before its star, starlight filters through its atmosphere like sunlight through stained glass. Molecules within that air absorb specific colors, leaving dark fingerprints called absorption lines in the spectrum. The James Webb Space Telescope has detected water vapor on the hot Saturn WASP 96b, steaming under 900 degrees Celsius heat. Sodium in HD 209458b's air, evaporating from its molten surface. Silicate clouds on the ultra-hot Jupiter WASP 17b, raining molten glass. But the holy grail remains: an atmosphere with oxygen, methane, and water in impossible balance. On Earth, that combination screams life. Elsewhere, we don't yet know. Weather follows physics, even when the ingredients are alien. On tidally locked planets, supersonic winds may howl from day to night sides. Gas giants with no surface could host storms that rage for centuries. Carbon-rich worlds might rain liquid diamonds through hydrocarbon haze. Consider HD 189733b, a cobalt blue world where winds scream at 8,700 kilometers per hour, 5,400 miles per hour, hurling molten glass sideways. Or Kepler 7b, where clouds of reflective minerals float permanently on the dayside, creating the first exoplanet map we've seen. What would truly shock us? Not just oxygen, but its presence alongside reducing gases like methane, a combination that shouldn't last without constant replenishment. On Earth, that means plants and microbes. On another world, perhaps something stranger. Purple bacteria dominating a red dwarf spectrum. Silicon-based life exhaling silanes instead of carbon dioxide. Subsurface organisms venting hydrogen into an icy moon's thin air. We might first detect such life through disequilibrium chemistry. Atmospheric mixtures that defy natural equilibrium, like a candle flame that never flickers out. For now, these atmospheres remain hypotheses painted in sparse data points. But soon, next-generation telescopes will analyze Earth-sized worlds. AI will sift through atmospheric spectra for anomalous patterns. We may even capture direct images of exoplanet weather systems. Every molecule tells a story. The challenge is learning to listen. Picture a world adrift. No sunrise colors its horizon. No solar winds stir its atmosphere. It floats in perfect blackness, untethered from any star. A cosmic orphan wandering the spaces between suns. These are the rogue planets, and they may be among the most common worlds in our galaxy. Astronomers estimate billions of these nomads wander the Milky Way. Some form like stars, collapsing directly from gas clouds too small to ignite fusion. Others get violently ejected from young solar systems by gravitational slingshots, a planet's ultimate eviction notice. Without a star's warmth, their surfaces plunge to temperatures near absolute zero. Yet surprisingly, they might not be entirely lifeless. Deep under icy crusts, 3 heat sources could persist. Radioactive decay in their cores, the same slow furnace that keeps Earth's interior molten. Tidal flexing from nearby moons like Jupiter's Europa, warmed by gravitational kneading. Primordial heat left over from their violent formation. These could maintain subsurface oceans for billions of years. On Earth, we find entire ecosystems thriving near hydrothermal vents, far from sunlight. Why not in the dark oceans of a rogue world? Imagine standing on such a planet. The day would last forever, an eternal starless night. Any atmosphere would freeze into snow, leaving the surface exposed to cosmic rays. The only light might come from bioluminescent life forms, if present. Distant galaxies smeared across the sky. Rare close encounters with other rogue worlds. Yet in that perfect darkness, something astonishing might exist. Life completely independent of starlight, drawing energy from chemistry and heat rather than photosynthesis. Detecting these worlds challenges astronomers. Microlensing. When a rogue planet's gravity briefly magnifies light from distant stars. Thermal imaging. Spotting their faint infrared glow in interstellar space. The Hubble Space Telescope's best direct image of an exoplanet shows HR 8799e as a single pixel, a pale blue dot without detail. The James Webb Space Telescope does better, revealing atmospheric components through spectroscopy, but still cannot show us mountains or seas. We're like nearsighted astronomers squinting through Galileo's first telescope, aware we're seeing something revolutionary, yet frustrated by the blur. 3 technological leaps may change this. Next-generation telescopes, like the planned Habitable Worlds Observatory, with star shades to block stellar glare. Optical interferometers combining multiple telescopes into one massive virtual lens. AI-enhanced imaging reconstructing surface features from atmospheric scattering patterns. The goal? To capture a pale blue dot, and then resolve it into something more. What might we see when technology succeeds? Continent shapes from reflected light variations. Cloud movements tracking weather systems. Vegetation red edges, or alien equivalents. In spectral analysis. Seasonal changes as ice caps grow and retreat. The first images will be crude, blurry patches of color and contrast. But with time, they'll sharpen into maps. And one day, perhaps, we'll point to a dark pixel and say, there, that shadow could be a forest. With this power comes responsibility. What if we detect unmistakable signs of life? Should we attempt contact or observe silently? How do we protect celestial objects from our curiosity? The answers may define our species' cosmic maturity. For now, we inhabit a privileged moment, poised between ignorance and knowledge. Like children pressing our noses against the glass of a candy store after closing time, we see only shapes and colors, not the sweets themselves. There's beauty in this anticipation, in not knowing, in preserving, just a little longer, the universe's capacity to astonish us. Consider this: when Columbus set sail, maps still held dragons at their edges. When Apollo 8 first orbited the moon, no human had seen Earth whole. Our greatest discoveries have always come with the realization that reality outstrips imagination. The exoplanet era's greatest gift may be this. No matter how many worlds we catalog, the universe will always hold more mysteries than answers. Thanks for watching. Please subscribe, like, and share. See you next time.